So today we're going to start talking, if you don't know, we're going to start talking about functions. Okay, we're going to define functions one more time for you, probably like, at least the third time in your mathematical career that you had the word function defined for you. Okay, we'll look at, identifying functions, again, just real quick, and then we'll talk about, as you can see, we'll get into those graphs of some basic functions, some parent function graphs and stuff. And then finally, we'll talk about transformations of those functions. Okay, so first things first, let me zoom in a little bit. Okay, like I said, we'll talk about functions here, and then we'll get to those graphs in a little bit. Okay, so a function from a set A to a set B, okay, is a relation excuse me, that assigns, so again, a function from a set A to a set B is a relation that assigns each element x from set A to one element y in set B. Okay, that's like, an official mathematical kind of definition there, right? In the short terms, maybe you can just say like every x goes to one y. Okay, maybe like in layman's terms there. Okay, so functions, right, are just kind of like rules that relate, two sets of things. A function doesn't even really have to relate numbers. It can relate other things besides numbers, but we typically, look at functions as relating two sets of numbers. Normally, the set of numbers that we're looking at is the real numbers, right? Normally, the set of numbers we look at would be the set of real numbers for the set A. That would be like the domain. To then that set B, that would be like the range there. Okay, normally the domain is all real numbers. Occasionally we do have things like domain restrictions, and we'll talk about like what type of restrictions we want to look out for on, let's see here, what are we talking about? On Wednesday of this week we'll talk about domain and range more in depth, and also I think domain restrictions on that day too, I believe, or we may just, yeah, I think so, we'll see. But eventually we'll get into like domain restrictions and stuff as well. But anyway, so we take every member, anything that belongs in that domain, the original set A there, every one of those like elements should then be assigned to only one element y in set B. Okay, and that's what makes a function. Okay, or in other words, every x goes to only one y, just one y there. Okay, so of course we have different ways to test functions, right? Okay, to determine if something is a function or if it is not a function. One way we have to do it, we can call it maybe the algebraically. We just basically check to see that each x is assigned to only one y. Okay, and so we'll just do two quick examples here of that, and we'll look at just a set of ordered pairs here, and we'll ask, is it a function? So that'll be our question here. Is it a function? Okay, and so for the first one here, we'll start with the set of ordered pairs. We'll see like -1, 6, 2, 5, 0, 9, and 3, 5. Okay, so here's a relation. A relation, believe it or not, is also kind of like defined mathematically, right? Okay, it's not just like relation and like, the sense, kind of the Englishy sense of the word or whatever. It's like actually a relation has a definition, and so then this is a relation right here. You can see that, -1 is related to 6, 2 is related to 5, 0 is related to 9, and 3 is related to 5, okay? We don't necessarily know the rule, like we don't necessarily have a rule for this, like we don't really know why -1 is associated with 6, why 2 is related with the 5, or anything like that. We don't know that. We're just given, here's a relation, okay? It's kind of just like, this is the reason why. Okay? Of course, other situations, right, where we have functions and stuff, we're given like a function rule, okay, where, we know if we're given any sort of x, we can plug that x into the function, and then it'll spit out an output, a y value. But in this case, it's just a straight up relation. We don't know why they're related this way, they just are. But is it a function? What do we say? Is it a function? Does every x go to only one y? Yes, yeah. -1, okay, goes to 6. 2, all right, goes to 5, 0 goes to 9, 3 goes to 5. So each one of those x values, the -1, the 2, the 0, and the 3, they all go to only one y value, 6, 5, 9, or 5, respectively, okay? The fact that 5 shows up twice is okay because it's different x values that are associated with it, okay? 2 is associated with the 5, so 2, the x value, the x value 2 goes to 5 and only 5, and 3 only goes to 5. Okay, so this one actually, yes, it is a function. Even though that 5 shows up twice, it's still a function. Okay. How about this one then? Let's do 6, -2, 9, 3, 8, 2, and then 6, 1. Is it a function? Is number 2 a function? Okay, so no. Okay, and so where does it fail? Where does it fail? Yeah, go ahead, Anna. Yes. Okay, so the 6, right? Okay, we have one x value, the 6 value 6. It goes to, or the element of 6, right? It is assigned both to -2 and to 1. So here you can see the 6 is paired with the -2, but 6 is also paired with 1. So no. Okay, it is not a function. Okay, it's not a function. The x value 6 is paired or related with 2 different y values. And so, of course, with there being a relation here, with there being a function, we're talking about x and y coordinates. We can then think about that graphically in the coordinate plane, right? We could represent this both of these relationships. We can represent exactly in a graph too, right? Rather than just like the numbers, we could also represent it in a graph. Okay. And so, if we were to represent this kind of like graphically, as opposed to algebraically, all right, the test that we have, right, to determine if something's a function or not is the vertical line test, right? Okay, and so the vertical line test, while it's easy for us to like visualize, I don't know, I'd never have been able to come up with a very elegant definition for it, but I'll just write it here what I've got. So if a vertical line passing any part of the graph of the relation intersects more than once, then the relation is not a function. Again, not very elegant, but you get the idea, hopefully, okay? So again, that's why, you know, when we graph our, like if you were to graph those ordered pairs there, right, that we had, the second set would fail because you've got the same x coordinate here, 6, and here 6 as well, but they both go to different y values. So you'll have 2 points that are kind of like above or below one another, and so a vertical line will hit both of those points and then result in then it not being a function by that vertical line test. Okay. So what about something like, you know, what are some other examples of that, right? What if we talked about something like, you know, our circles, right? Let's say we had a circle, you know, x squared plus, I'm just going to make up a circle here, y minus 2 squared equals 16. Okay. Believe it or not, we can graph this. We haven't really, well, besides, you know, just grab my hand. We can actually, like, get this into a format where we can graph it in our graphing calculator, right? Right now, the way it's written, we can't graph that in our graphing calculator. We don't have, it's not solved for y, right? You need to have y equals. So we can solve this for y. We'll subtract x squared from both sides here. We get 16 minus x squared. Okay, and then we'll square root, right? We gotta get that y by itself. So we'll square root both sides because we just need y. Okay, so we square root there, and we get y minus 2 equals, and then the square root of 16 minus x squared, that quantity. Again, we can't break that difference up. We can't break up the subtraction. We can't say it's equal to the square root of 16 minus then the square root of x squared. We have to keep it that same, that whole quantity. Also, because we're in an equation setting, we need to put a plus or minus in front there. Okay, plus or minus. And then we can finally add that 2 over, and so we get y equals 2 plus or minus the square root of 16 minus x squared. Okay. And so now we can graph this. All right. And so to graph a plus or minus in your graphing calculators, all right, if you want to follow along here, you can't, or at least I think there is a plus or minus button, I believe. Let's see here. There's like a plus or minus kind of command, but I don't think it works in y equals. Pretty sure I saw a plus or minus. Maybe I didn't. Nope. Okay, I guess I was wrong. I thought I had seen plus or minus before, but I guess that doesn't show up. Okay, never mind. Cool. So anyway, to graph this, then we'll just why does it do this? Okay. We'll graph two separate things. In our y1, we'll do 2 plus, okay, the square root of 16 minus x squared. And then in y2, we'll do 2 minus the square root of 16 minus x squared. Okay? And so it should look something like that. We'll just graph 2 different pieces. Alright, and then if I hit zoom 6, okay, there's our graph. Not very good, okay? But there's our graph. Okay. Even though the graph is not complete there, we can certainly see whether this is a function, right? Does this pass the vertical line test? Yeah, no, it does not, right? It's not a function. But again, we shouldn't be surprised by that, because if you think about it, if I just pick any x value here, let's just say I pick an x value of 0, okay? 0 squared is going to be 0. It'll be 16 minus 0, 16. Square root of 16 is going to be 4, but then the y value that's going to match to that 0x value is going to be 2 plus 4 or 2 minus 4. So there's going to be 2 different y values that are matching back to that same x value. So of course this thing can't be a function. We have 2 different y values for certain, at least where x is 0, right? And so it's not going to work. So there it is. If you want to try and adjust this, because obviously we know we're supposed to get a circle here, this looks more like an ellipse or an oval or something like that. To fix that, you got to remember here that your graphing calculator, right? Okay, the window is a rectangle. A rectangle. I don't know why I emphasized that other part of the word. Anyway, so there it is, okay? So the problem is, though, your standard viewing window for the graphing calculator is negative 10 to 10 on the x and negative 10 to 10 on the y. So in order to make it fit in this rectangle, the negative 10 to 10 on the x has to be stretched some because it's a wider, amount of space we have to cover, whereas, the top to bottom, that negative 10 to 10 is going to look more squished because it's a smaller, it's shorter. So there's a way to fix that. If you press the zoom button and go down to I think it's zoom square, that will automatically adjust your window to make it kind of square up so that it, it should fit more nicely. Again, you might be wondering why the graphing calculator isn't drawing the full part of the circle there. I think it's because the graphing calculator, with the way that it graphs things, since those pieces that are missing would essentially be vertical, I guess, to one another, and the way, again, the graphing calculator chooses which pixel to color in and which one not to color in, it just doesn't color those pieces in. Okay, but if you were to zoom in on these sections, right, you would see that they do, in fact, like join up, okay, on the graphing calculator. In fact, there's another zoom command called zoom box. I don't know if you ever used this one before, but if you use your arrow keys, you'll see you have this like little target thing, and you can actually like hit enter. It'll drop a point, and then it'll kind of like allow you to create a little box, and then hit enter again. It'll zoom in on that box, and you can see that it does. You see it gets closer, right? And you can zoom in again if you wanted to, again using that zoom box. And you'll see that they do get closer and closer there the further we zoom in. Oh, that one doesn't look too bad. But anyway, so you can see they still have that. This still doesn't want to draw that space there, but we know they should connect and stuff. Okay, and then back to zoom 6 for our little football there. Okay, so there's that. All right. So any questions on function testing? Again, algebraically or graphically? I think we should be good on that. Something you guys have seen since, forever, at least since Algebra 1 for sure. Okay, if not, then let's get out that, excuse me, the graphs of basic function, that paper that Abby passed out to y'all. This guy right here. Okay, and we're not gonna, well, maybe we will. I don't know, we'll see. Maybe not. Maybe not. Okay. So we're gonna first of all, for some basic functions, we again want to have like a basic understanding of some of these more typical functions that we'll be seeing. So for example here, right, a typical function that we'll be seeing is the identity function, which is kind of just a fancy phrase for the function y equals x, right? We're just looking at the graph of y equals x there when I talk about the identity function, okay? Or maybe I should really say f of x equals x here. I guess because we're talking about functions, maybe like the function rule, f of x equals x. Okay. And of course, the identity function, right? No surprises there. I mean, we can graph it if we need to and see here. But it's just going to be, it's just a line. Y equals x, right? It's the slope of 1. Y-intercept is 0, right? That is slope-intercept 4 there. And so you can just kind of sketch this to look, something like that. I'm not even going to bother putting in, coordinates or anything like that, which is maybe bad math. Okay. So that's a graph we want to be familiar with, and we're going to, maybe perform some transformations on that. Harder to see the transformations though with the identity function. But absolute value function, all right, that's another function we should be familiar with here. Again, we'll say f of x equals the absolute value of x. That's that absolute value function. Okay. Of course, that's like, it's going to look the same. So it's going to look the same as the identity function to the right of 0. Okay, it looks the same as that identity function to the right of 0 because all those x values, all those positive x values here, right, that gave us these matching positive y values over here, right, that's going to be the same thing here, right? The positive x values, absolute value of a positive number is still a positive number, so we still get that piece. Excuse me, but then the left-hand side here, where we have these negative x values that are supposed to then match to these negative y values along here, well, since we're taking the absolute value, it's going to take all those negative y values, where we have those negative x values, and it's just going to make them now positive. So it flips it up and creates this V-looking shape. These y values stay positive, and these y values that were negative now become positive because now we're taking the absolute value of that x. So it took this part, this negative part of the function for the x, or for f of x equals x, and now it's going to just flip it up, reflect it over that x-axis and flip it up. Okay, so that's how we kind of get that absolute value function, that weird kind of thing. And of course the slope, right, if you talk about the slope of this thing being 1, the slope of the absolute value function, right, for the For the increasing piece, that's a slope of positive 1. Right? Same kind of idea as that slope. And then the slope for this piece right here will be a slope of negative 1. It's going down 1 and right 1. Okay? Square root function, that's f of x equals the square root of x. Okay. Here I will put in a few coordinates just to kind of help us out. So of course, we don't have anything to worry. We don't have any like negative x values that we can plug in there because it'll be imaginary. We want to keep the graph real here. We're going to start with 0. 0 is the lowest x value we can start with, right? Because anything else will be negative. But the square root of 0 is going to be 0. So you end with the point at the origin. There is where we start. So the square root of 0 is 0. Square root of 1 is 1. So we have that point right there. 1, 1. Right, and then the square root of 4 is 2. So I'm going to go 1, 2, 3, 4 out to that, and then we'll put it right there. And so the graph kind of looks like, okay, like that right there. And it's just going to continue on. Okay, so there's the first example of a graph that has a restricted domain, right? Here, the x values could be anything. Here, the x values could be any x value, but here we can't pick just any old x value. We have a restricted domain. We don't want to take the square root of a negative number there. Okay. And then related to the squaring function, we have, or related to the square root function, we're going to have the squaring function, or there's just x, which is just f of x equals x squared. Okay. Which, again, I'm not going to worry too much about coordinates here. I'm just going to draw this one because this one's so familiar, hopefully, to us. It's a parabola. Okay, it has a vertex at the origin there, so it's going to look something like that. Okay. And of course we have then the cube, so f of x equals x to the third, okay, which is slightly different now because now when you cube positive x values, you're going to end up with a positive y value. But if you cube negative x values, we'll have negative y values. So whereas with the squaring function, right, if you square a positive or a negative number, they'll both yield positive y values, positive function values here. So that's why it's always positive, right? Here, the cube is going to give you both positive and negative values depending on where you wrap. So I'm going to try and just graph this. Okay, like that. So there's f of x equals x cubed there. That's a transformation of that. And then, again, has a vertex, kind of a central point there, or I don't know if I call it a vertex, but a central point there of 0, 0, right? And then finally, we'll look here at the rational function. We're not going to worry so much about sine and cosine right now. We'll maybe come back to those much later. But the rational function, that's 1 over x. Okay? That's 1 over x here. And what x value here is going to give us a lot of trouble? 0, right? We can't divide by 0, right? It's undefined. The function will be undefined. So at 0, okay, we're going to have a vertical asymptote. So if you want to draw that in, you can. Okay. We also are going to have a horizontal asymptote at y equals 0 as well. So if you want to draw that one in, you can too. Okay. Horizontal asymptotes and vertical asymptotes, though they are both asymptotes, right, they have slightly different behaviors. So for example, horizontal asymptotes, there are times, situations where you will cross a horizontal asymptote, but you will never cross a vertical asymptote here. So we'll just graph this piece, and so the function is going to look something like this. Okay, like so. And so again, you can kind of see there is kind of a central point there. The origin is kind of a central point. It's just where the vertical and horizontal asymptote kind of crisscross. Okay, from there. But there it is. And again, we'll worry about sine and cosine a little bit later in this class. And by a little bit later, I mean quite a bit later, actually. So we'll come to those in a later time. Okay? So there's those. All right. Now, flip your paper over, and we'll talk a little bit about transformations. Transformations. Okay? All right. So, let me see here. Yeah, okay. Transformations of functions. Okay, and I might do this in a slightly different way maybe than you saw it in Common Core or Algebra 2 or something like that. I'm just going to focus like on individual pieces here, and then you can kind of put things together. But for example, let's just start out assuming that C is greater than 0. Okay, we're going to have this number C we're going to use it's greater than 0. Okay, so for example here, if we have f of x and then we add that positive C value on to the end there, so f of x plus C, okay, how does that, does anyone remember, how does that affect the our function? Or what's that going to do to our function to add that C value onto the end of our function? What is that going to do? How does that transform the function? What happens to it? Yep. Vertical shift, right. And up how much? Yeah, whatever the C value is. Exactly right. Yeah, so this is going to result in a shift up C units. Okay, and so of course, if we have plus C, then we'll also have the minus C there, and so a minus C would make sense to shift down, right? So we're going to shift down C units. Okay. What about f of the quantity x plus C, though? What does that do? Again, if C is a positive number, what does that do? Is that okay? Not a stretch. Nope, not a stretch. Good thinking, though. Good, because we will look at that. We will look at something like that. Actually, we're not going to do horizontal stretches too much. We will talk about vertical stretches, though. But yeah. Yes, it shifts it, okay? And specifically, if C is a positive number here, so if we have x plus C, which directions are going to shift it? To the right. So, right, intuitively, right, we would think it's going to shift to right, but actually this shifts left, okay? If our C value is positive here, we have x plus C, it's going to be a shift left. C units. And I'll just show you that here real quick. I'll put up a graph of x squared here. Okay, so there's the graph of x squared, right? And so within that, then I'll say, you know, x, I don't know, plus 5. And then we'll square that instead, okay? So again, we're going to add a positive C value there. And you can see it actually shifts it left. See, so it kind of does backwards to what you would think. You think, oh, plus 5 is going to shift to right 5. No, it's actually shifting left 5. Okay? That's the idea there. And so then, if we have f of x minus C, that'll shift things which direction then? What will that shift in? Which direction? To the right. To the right. Okay. Let's see some other things here. If we have negative f of x, negative f of x, so negative in front of the f of x like that, how does that affect our graph transformation? What does that do to the graph? Negative f of x. So any y value that was positive now will become negative, and any y value that was negative will now become positive. So what's that going to do? Well, let's take a look here. So again, we have x squared, and we take that and make it negative x squared, like that. Okay. Okay, there's the graph. So how will we describe that? What happened there? Yeah. Reflection, exactly right, over the x-axis. Exactly. And so then we can also reflect over the y-axis as well, and that's f of negative x. Okay, so that's a reflection over the y-axis. That's how you can reflect it over the y-axis there, too. Okay, let's see, I want to talk about two more things here. So, how about c times f of x? Okay, if you put like a constant in there, c times f of x. And there's kind of two scenarios here that we're going to worry about. So if it's if c is, well, obviously we said c was greater than 0, but if c is actually greater than 1, okay, so we multiply that function f of x there by c. If c is greater than 1, that's going to be a vertical stretch. Okay. A vertical stretch. So in other words, you know, a coordinate x comma y will become same x coordinate, but now it'll be c times y. Okay. C times y. So it stretches that y value. The x value will stay the same, but then the y value will just get stretched up some. Okay. If c is between 0 and 1, it won't be a stretch. What will it be? Shrink. It's going to shrink, right? Because again, you're taking a fraction of that value, so it's going to be a vertical shrink. Okay, but again, it'll still take that xy coordinate, and then it's just x comma c times y. But again, if the c is between 0 and 1, it's going to result in a shrink, right? It's going to get like, you know, if it's like the c value, for example, is like 1/3, the y value is 1/3 of what it originally was. Okay, we can kind of see that here too. So let's just do like a vertical stretch here. So 2x squared. Graph it. There's the original function. There's 2x squared. You can see it's stretched up some there. Okay. And of course, if we have like, let me do 1/2. Okay, so 0.5x squared. Again, just to show the vertical shrink. If you can there, it's like smushed down a little bit, half as much. Okay. That's the idea there. Okay. So let's do a few examples here. I'll do 2 examples with you guys, and then I'll have you try one, and then we'll get started on the assignment. All right. So just do 2 here. So we're just going to sketch the graph of g of x here. Okay, that's our direction. Sketch the graph of g of x. Like I said, I'll do 2, and then I'll have you guys try one here. So number 1, let's do g of x equals negative x cubed minus 5, like that. Okay. Negative x cubed minus 5. So we got a couple things going on here at once, right? First, I see a negative, okay, x cubed right there, which means we're going to be reflecting over the x-axis, right? There's a negative kind of in front of our function. Our parent function here is the function x cubed, right? So this is like this gx is a transformation of x cubed. So we have a negative in front of that x cubed, which means it's going to be a reflection over the x-axis, and then this minus 5 is going to shift it. Right? See, f of x minus 5 means we're going to shift it down c units. So we're going to shift it down 5 units. Okay? And so, So normally our graph would go up and through the origin like that, right? Okay, we go like that. That's like our normal x cubed. But we got to go down 5. So 1, 2, 3, 4, 5. And then instead of going up from left to right, we're going to go down because it's reflecting over the x-axis there. So 1, 2, 3, 4, 5. There's our kind of like new point that we've got. And we're just going to go like that, reflected over the x-axis, and then shift it down 5. So there's our graph. Again, I can draw like the original here. Let's see, what do we red maybe or something like that. So there's our original. Okay. So you can see we went down 5 and then reflected it over the y-axis to make it go that way. Alright, try one more here. We'll do g of x equals negative x minus 2 squared plus 1. Okay. And so, Julia Regal, what kind of transformations do you see here for number 2? Okay, another reflection across the x-axis. Anything else? Right, 2 units, and also up 1. That's right, very good. Okay, so again, we'll just count that over. So 1, 2 over. We're going to go 1 up. So there's kind of like our new point there, the new vertex for that, again, x squared. So you have to remember what the graph of x squared is, right? It's a parabola. Parabola normally would kind of be like a U shape, but now because it's reflecting over that x-axis, it's going to be upside down, so it's going to go down like that. Okay, and so there's our... Again, we're just sketching. We're just sketching here, so just trying to get an idea exactly what the shape looks like and stuff. But there it is. Alright, let me have you guys try one here. So this last one here, and I'll get you guys started on your assignment. Okay, so try this one. We're going to do g of x, excuse me, equals x plus, the absolute value of the quantity x plus 3 minus 3. Go ahead and give that one a shot. Number 3, g of x equals the absolute value of x plus 3 minus 3. Alright, good. So all good things here. So again, I'll just show you there's the picture, okay? Shifted left 3, down 3, okay? Again, that x plus 3, the number that plus 3 in with the x, it goes kind of like the opposite direction, okay? If all else fails, right, so if you find yourself at one of these problems, you're like, I have no idea what to do, you can always fall back on taking some of those, just going back to the original, taking some x values, plugging in those x values and then getting the matching y values, right? So you can just do, you know, like, I don't know, -1, -2, you know, 0, 1, 2, whatever you want to plug in, and then get those matching y values and just plot the points to help you try and get an idea what that graph is going to look like. And hopefully, you know, you can maybe figure out from there too. Okay, you can always fall back on that as well. All right. Any questions on any of that? All right. So let me give you guys your assignment then. Okay. All right. The assignment will be page 48, numbers 11 and 13. Page 61, numbers 17 to 22, and page 79, numbers 12, and then 15 through 18, but only do A and C. Okay, just do the A and C part there, okay? So 48, 11 and 13, 61, 17 to 22, 17 through 22, page 79 on number 12, and then 15 to 18, but only parts A and C for those, okay? And I'll kind of come around here and help you with anything you stuck on.